So in chapter 8 we will learn about normal subgroups and quotient groups. Basically we will generalize what we learn about congruences in Zn when we worked in modular arithmetic in Zn, and we worked in congruence classes, and we showed that congruence classes, every two of them are either disjoint or they are identical, and so on. We will generalize these topics to groups, and we will start this generalization as following in this example. So remember that we say two integers a and b to be congruent modulo 4 if 4 divides their difference. We remember that, right? Which means a minus b is a multiple of 4, which means a minus b belongs to this set which we call K, because multiples of 4 are either 0, plus minus 4, plus minus 8, plus minus 12, and so on. So we will say that two integers a and b are congruent modulo 4 if and only if their difference belongs to K. So this is the idea, this is the generalization. We will say two elements in a group are congruent if their difference lives in K. What is K? It will be some subgroup. Now if we go here, the subgroup K, we mean actually this K is subgroup of Z, remember? And it is actually, we wrote it before as 4 times Z. This is a subgroup of Z. And now taking two elements from the group Z, we are working here with addition. Taking two elements, we will say they are congruent modulo this subgroup if their difference lives inside this subgroup. So we started generalization here. So again here we will say a to be a congruent to be modulo K if and only if their difference lives inside K, and K here is still the subgroup generated by 4, which is 4Z. And now we will use this to generalize the definition of congruent element to groups in general, not only Z. And this is the way we do it. Now if we start with G, a group, and choose any subgroup K, a subgroup of G, then we will generalize the last line, which means this line here, to define congruent. How two elements, what does it mean for two elements to be congruent modulo subgroup J? But before we move, we want to agree on the notation of the operation of the group. For the additive notation, we write a plus b, and 0 is the identity, and negative c is the inverse, and a minus b means a addition the inverse of b. So this is the idea. In here it is addition. Now the analog for it in multiplication, it is a multiplied by the inverse of b. So in here it is a added to the inverse of b, because we are working with addition. But now working with multiplication here, we will say a multiplied by the inverse of c. Okay, so instead of using a minus b, I mean for addition we will say a minus b belongs to K. That means a and b are congruent modulo the subgroup K. But when the operation of the group is multiplication, then we will say a times b inverse belongs to K. That means a and b are congruent modulo K. So this is the way we will define congruence in groups. And here we go. This is the definition. We start with K subgroup. You can choose any subgroup of a group G. Then A and B, any two elements from that group are congruent, or we say A is congruent to B modulo K if AB inverse belongs to K. And now here we mean AB inverse, we mean A star B inverse, okay, belongs to K, and the star here might be addition. In such a case, if a star is addition, this will be A minus B belongs to K, and if the star is multiplication, that will be A B inverse belongs to K. Okay, so let's go back to the definition. A is congruent to B modulo subgroup now K. This happens if and only if this is equivalent for saying A times B inverse belongs to K. So this is the definition of how two elements are congruent to each other modulo a subgroup K. You may say congruent to each other with respect to a subgroup K. Okay? And now in blue here, any pair of elements of K are congruent. Why is that? Because if we choose, let's start with a subgroup K. Take two elements from inside K. Then R1 and R2, say R1 and R2. Then R2 inverse lives inside K, right? Because K is a subgroup and R2 is an element of K. So R2 inverse live inside K, and R1 is from K. Now multiply them. R1, R2 inverse. It all is still in K. And so let me write that. This is because R1, R2 inverse will always live in K for all R1, R2 elements from K. So any two elements inside the subgroup are congruent to each other. Okay, so let us see now. Again, two elements inside the group are congruent to each other if AB inverse lives inside that subgroup. Now let's see an example. Let us choose K to be the subgroup of D4, this subgroup. Okay, R0, R1, R2, R3, these elements represent the rotation in the dihedral group of order 4. Now this explains that D inverse is D, and H times D inverse is H times D, and that equals R1, and it belongs to K. So what we got here, H times D inverse belongs to K. That means H and D are congruent modulo K, where D is given this way. This is D, so it equals its own inverse. This is H. Now compose H compose D. We will have now computed. Let me write it here. For sure, H compose D. Make sure H compose D. Sorry for that. H compose D. Yep. Okay. Equals R1, which belongs to K, and therefore we will say that H and D are congruent modulo K. Okay. In here, I would like to bring the dihedral group D4, and let us play with it before we keep moving. Let's have fun playing with the D4. So this is the multiplication table of D4, and again our group is, the group we are working is with is R0, R1, R2 and R3. This is the subgroup of D. Okay, now we have seen that H and D are congruent modulo K, correct? What about D and T? D and T, let's work with them. D and T. So we will see D and T. Let's multiply D times T inverse and see if that is in K or not. So what is T? So in here I'm not giving you the permutations. I'm giving you the table of composition, and we will use it right away. So the question here, let me write it. Are D and T congruent? This is U, congruent modulo K. So this is the question. So how do we, this question it is translated to the following. D is congruent to T modulo K. So this is our question. And this is equivalent for saying or for asking dt inverse. This is compose T inverse. Is that in K? If yes, then they are congruent. If no, then they are not congruent. Okay? Let us play with that. What is T inverse? How I get the identity? The identity is R0, right? So what do I multiply T with what I multiply to get R0? If you look in here, this is R0, and simply you will find T inverse is the same as T. Now if you recall that each of D, H, T and V, they were reflections. Then when you do reflection and then you reflect again, you get back to the identity to where you were at the beginning. So reflection and deflection again, you get the identity. So each one of these D, H, T and V, each one of them is its own inverse. Okay, now let's see, decompose T inverse. That means we want to compute decompose T. And what is decompose T? So this is D here, this is T here. Take the composition of them, we'll get R2. So this is R2. Oh, okay, so it belongs to K. Good. So this is, the answer here is yes. Okay. Now let's ask another question. What about D and V? Is it congruent? Are they congruent modulo K? So let's play them. Now do them for quick. The inverse of D, of V, decompose V inverse, but V inverse is V itself. So decompose, this is D and this is V. Decompose V is R1. So it belongs to K. Oh, okay, good. So this is also yes. So D is congruent to H and to T and to V. Oh, okay. What about H and T? Compute it, and then you will find H and T are congruent modulo K. This is true. And what about H and V? And you will find this also. And what about T and V? And you will find that. So make sure each one of these is correct, the same way as I did it. Now what I concluded here in this example, that H, D, T and V, any two of them are congruent modulo K. Good? Okay. And if we go back to K itself here, any two of the elements of K are congruent modulo K, because we just have that written in blue. So we have two sets of elements of D that are congruent. The elements of K, each two of them are congruent to each other, and the other elements H, D, T, V, each two of them are congruent to each other, and that will have a meaning for us within a while. So let's go back. We will use this. We will be back to it. Let's go back to the definition and the theorem after the definition. Okay, so we got the definition. Now this theorem is not very new, because it generalizes what we have seen in Zn. If K is a subgroup of a group G, then the relation of congruence modulo K is, so it is a relation. Two elements are related if they are congruent modulo K. First, every element is congruent to itself modulo K, right? Because A inverse. So this is the proof of this is so easy. A times A inverse is the identity, and the identity belongs to K because K is a subgroup. Okay. Now, if A is congruent to B, then B is congruent to A. So what is the proof for that? If A is congruent to B, then we have, so I have some space here. A is congruent to B modulo K. That means A times B inverse belongs to K, right? And that means A times B inverse equals small k for some small k belongs to the subgroup K. Okay, what do we want here? We want B times A inverse belongs to K. B times here, let me write it in green. To prove that, we want B times A inverse to belongs to K. This is what we want to prove. Can we do that? Can we obtain that from here? So take the inverse of both sides of this equation, then we will get B A inverse equals K inverse, right? And that belongs to K because K is a subgroup. Okay? And then we are done. Then B is congruent to A modulo K. Good. Now to prove part 3, it says A is congruent to B modulo K. So we have A, B inverse belongs to K. And also we have B is congruent to C modulo K. So we have B, C inverse also belongs to K. And we want AC inverse to belongs to K. Okay, so can we do that? So easy and quick. How we do this? Now notice this belongs to K and this belongs to K, two elements, so multiply them. So we must have, multiplying these two elements, both of them are from K, it must belong to K, right? Since I did not write that, I said K is a subgroup of G, and this statement should be written everywhere in here. Okay, and now multiply these two, use Ising associativity, then we get A C inverse belongs to K, and this is what we want. So the theorem is proved. Now again, as we said at the beginning of the lecture, what we will be doing here is generalizing the idea of congruences and congruent classes that we have seen in chapter 2 when we worked with Z or Zn. And this theorem is a generalization of theorem 2.1 if you like to go back and see it. Okay. So we start again with K as a subgroup of G. Now the idea here pick an element. Let A be an element in G. So what we do with A, we will define the congruence class of A modulo K. How we do it? So what's happening here? We have a group, bigger group, say, and we are assuming we have a subgroup K. Okay. Now we picked an element from the group. It might be from the subgroup, and it might be from outside subgroup. Okay. Now I'm asking this element A. I want to call all elements in the group G that are congruent to A. So I will keep picking elements that are congruent to A till I finish, and then get them together. Then I will get the set of elements of G that are congruent to A. All the elements of G that are congruent to A. I will collect them in one set, and I will call it the equivalence class of A modulo K. If I work modulo some other different subgroup, then the congruence class would be different. So I cannot say the congruence class of A and then stop. No, I have to say modulo what? So the congruence class of A modulo the subgroup K are all these elements that we have collected. It is in here. So I will choose B from G or element that are congruent to A modulo B. So this I have A in here. Then I collected all elements that are congruent to it. So every time I called it B. So to have an element B congruent to A means BA inverse is in K. Okay. So BA inverse equals some small k. Okay. Multiply both sides with A, we get B equals KA. Oh, that's interesting. So I will choose all elements from the group G such that every one of them is a multiple of A, where multiple means here multiplying A by some element of K. So multiple of A with respect to K, I may say. So it is this way. So good. So again, I have a group, subgroup K, and an element. And I collected all elements that are congruent to A. And surprisingly, after this collection, after I got this set, they came out to be simply the subgroup K multiplied by the element A. So in the group G, one element A, if I want to call for all elements in G that are congruent to A, simply I will take K, all elements in K, and multiply them by A. Then I get that set, the congruence class. So here we go now. We define the congruence class of A modulo K is simply came out to be just multiply the subgroup K by A. Subgroup is set. How we multiply a set by an element? Simply multiply every element in that set by the element A. Okay, so we got the congruence class of A modulo K. Let me make a graph for this at this side. Let's play with it a little. Let's have fun with that. Say this is the group G. Okay, and the subgroup K somewhere here. Pick an element from outside A. We can define the congruence class of A if we choose it from inside K. This is no problem. But in fact, if we choose it from inside A, then the congruence from inside K, if we choose A to be here, then KA will be K itself. So this will be trivial, because we said any two elements inside a subgroup are congruent, And if you take an element from the subgroup itself and call all elements that are congruent to it, they will just be simply the subgroup itself. Now, so let's choose an element from outside K, and now I want to make a representation, a sketch for the equivalence class of A. So I will choose elements from the group. I will take elements in the group. One of them might be here, some other here, some other there, and each one of these is congruent to A modulo K, and we have seen that means each one of them equals A times an element from K, correct? So let me collect these elements together. So let me go back and take these dots away. So simply Ka, the congruence class of A modulo K will be simply Ka. Okay, so we multiplied K by A, and A shall live in that congruence class. Why? Because the identity lives inside K. The identity lives inside K because it is a subgroup. And A times K, then we will have A times the identity being there. Okay. Let us go back to see what are the congruence classes of inside Z. An example in here. Let us say Z, this is our group G, and let us choose K to be 6Z. Okay, so what is the congruence? Now the operation here is addition. Of 5, the congruence class of 5. It is K. Now I will write star 5. Okay, or K5 if you want. Okay, yes, I can write it this way. K5. Okay, that means I'm using this notation here, K5. But the star here is addition, and so we have 6Z plus 5. And you have seen this equivalence class before. 6Z plus 5, and it consists of 5, 11, 17, and these are the elements that 6 divides the difference between any of them. What about the equivalence congruence class of 3? 6Z plus 3, and you know what that equals. What about the congruence class of 1? And here we go. Good, so we have seen these things before. Now let me go back. Okay, no, let me continue here. I want to write down all the equivalence classes of K in here in this example. So we have the equivalence class of 5. This is 5 here, and of 3, and let's have of 2, and the equivalence class of 4. And what is the equivalence class of 0? Is 6Z itself, right? Okay, and we have seen these things in color before. Now I want to ask you, the definition of congruence class started with the subgroup K, which is 6Z here, but also it is started with any element inside the group Z in here, any element. So 7 is any element, So what is the congruence class of 7? Which one of them is the congruence class of 7? We'll have learned that this is the congruence class of 7, and this is the congruence class of 8, and this is the congruence class of 10, and this is the congruence class of 9, and this is the congruence class of 6, and this one is the congruence class of -1 or of 11 here, or of -1. So let me remind you of something that we learned before. Let me bring it here. So here we were working with K to be 6Z, and the group G was Z itself, and the black color here represents this subgroup, and it is the same as plus 6 plus 12, and here they are. This is 6, this is 12, and same thing, this is the congruence class of 1, which is the same as congruence class of 7, which is the same as congruence class of -1, and so on. And look at these things here. Okay, and now we will move to a theorem which says that every two convex classes are either identical, the same convex class, or they share nothing, they are disjoint. And we have proved this thing for when we worked with modular arithmetic in Zn, but we will prove it for general groups when G is any group and K is a subgroup inside it. Okay, now let's have more fun by going back to D4. I want you here in D4 to find all the equivalence classes, or I mean the equivalence class of every element in D4. The equivalence class we are working here with the subgroup K, which consists of R0, R1, R2, and R3. Okay, so what is the congruence class of D? In here, how we compute the congruence class of D? Simply, the congruence class of D will consist of, so let me write that. It's simply KD, right? And that means K compose D, and that means we want to find R0 compose D, right? And then R1 compose D, and then R2 compose D, and then R3 compose D. Compute them all, and for sure the result will be D. Not in order. Okay, we have them here. We want R1 compose D will give me H. Okay, good. So H. Now R2 compose D will give me T, and R3 compose D will give me V. So this is the congruent class of D, and this is not surprising, right? Because we have just to prove that D is congruent to T, and D is congruent to V, and D is congruent to H. So it is expected that D, T, H, and V are in the congruence class of D. Now let me ask you, what do you expect if I asked you to compute the congruence class of H? Would it be the same as the congruent class of so the recording did not record what I want here. Okay, so this the part I wrote in red was not recorded. Okay, it will be now recorded. Now let's compute the congruence class of the congruence class of congruence congruence class of H is KH, and again it is K compose H, which is R1 compose H, R0 compose H, R1 compose H, R2 compose H, and R3 compose H. Compute them all. So here H is, so R1 compose H is T, R2 compose H V, R3 compose H is D, and R0 compose H is H itself. So we will have H T V D. Oh, it is the same as congruence class of D, and it will be actually the same as the congruence class of T, which is also the same as the congruence class of V. So okay, so modulo the subgroup K, which consists of, so that we can see it here, of R0, R1, R2, R3, modulo this subgroup, D4 has two congruence classes, K itself and this one here, which is KH or KT or KD or KV. So we have two congruence classes. So D4 consists of two congruence classes. This is one of them, the subgroup itself, and the other one we can just write it K K using any one of these, KD, and it is D H T V. And now if you notice, D2 has been splitted into two congruence classes modulo K2. Okay, good. What is the order of D4? When I said D, I mean D4. It's 8. What is the order of the subgroup that we have computed the congruence classes modulo it? It's 4. So how many congruence classes are the congruent classes are there? 2 of them. This is 1, this is 2. So is that related to the order of the group divided by the order of the group divided by the order of the subgroup give us the number of congruence classes? And the answer will be yes. And we will see that in a theorem. So okay. So we have seen in theorem 2.3 that if two integers are congruent modulo n, then they share the same equivalence class. They give the same equivalence class. Same thing applies to our new definition for groups and subgroups. Now in theorem 2.3, it says the following. Again, if we have a subgroup K, a subgroup of G, and we have two elements in G, such that if they are congruent, then they give the same equivalence class, and this is if and only if. So I would like to write it here again. A and C are congruent modulo K. That means they give the same equivalence classes. The equivalence class of A is the same as the equivalence class of C. And how we prove this theorem, the proof is so quick. So let's prove this direction. Then we have A congruent to C modulo K gives that what A C inverse equals small k for some k. Small k belongs to the subgroup. Okay, and what that means, remember here, we want to prove for this direction, we want to prove Ka equals Kc. So what we do now, every element in Ka is an element in Kc. So okay, so what we get here, Okay. Okay. Okay, so we have this AC inverse equals K. That means A equals K times C, correct? And now we want to show that K times A, okay, let me see. Okay, 8 equals KC. Now, K times A equals K times KC, right? The big A is the subgroup, correct? Now, and this is contained, I say it is contained in KC. Do you know why? This is a subgroup. So let me explain that. Any element lives here. It's very trivial. Has the form K1, any element from subgroup K1, subgroup K, and multiply it by small k and then small c. And then by associativity we have K1 times K times C. But this one lives inside K, capital K, right? So this belongs to KC. And then we are done. So KA belongs is contained in KC. Now similarly, since similarly we will show that KC is contained in KA. Now I want more space, so let me move here. So we have showed KA is contained in KC. Oops. Now A is congruent to C modulo K. That means C is congruent to A modulo K. Right? We have just proved it. And this means CA inverse equals K for some. And now we will do same thing. We'll repeat same procedure as we done here. So that will mean KC is contained in KA, and then we are done. We have this here, and we have this here, and then we get KC equals KA. So we proved this direction. Now to prove the other direction, assuming KC equals KA, and then we want to show that K and C are congruent modulo K, A and C. Assume KC, let me see, KA equals KC. We want to show that let me write it. Want to show that AC inverse belongs to K, and then we are done, because that means A is congruent to C modulo K. Okay, now since they are this equals, then and the identity belongs to K, so multiply the identity here as one of the elements. So E times A, it belongs to K times A, right? But K times A is the same as K times C. And now we got A belongs, here it belongs, to KC. And this means A equals, say, K1 times C for some K1 inside the subgroup. And that means AC inverse equals that element K1, which is in K, and then we are done. So we proved what we want here. Okay, so the proof is very easy, but I got confused. Okay. Okay, now we want to remember that two elements, congruent element, give the same equivalence class. We will need that. Two elements, they are congruent modulo key, then they are k, sorry, then their congruence classes modulo k are the same. Okay. Now, in this theorem, we prove that this says. Okay, so the congruence class we defined here, the congruence class of O modulo k, just we worked, simply we call it right cassette. When we say right cassette, then that means equivalence classes. If you notice here, now right cassette is k times a, okay, but we actually means k star a, k star a, where star might be multiplication or might be addition. In here, look at the congruence classes or the cassettes, the cassette of 6z. This is the cassette of 6z, the cassette of 4 modulo 6z. This is the cassette of 2 modulo 6z. This is the cassette, right cassette of 1. This is the right cassette of 3. So right, we are saying right because a is coming to the right. We will say the left if a comes to the left of k. So these are the right cassettes. They are the same as congruence classes. So let a and b belongs to G. Okay. Because cassettes, right cassettes, are formed using a subgroup and an element. So two right cassette means a right cassette of A and a right cassette of B. Now we will show that want either Ka equals Kb or Ka intersect Kb is phi. Okay? Okay, so let's assume this is not happening. Assume Ka intersect Kb is not phi. And then we want to prove they are identical. Okay? That means if they are not empty, the intersection is not empty, that means there is an element C which belongs to their intersection. So the element C is congruent to K to A modulo K. That means AC inverse belongs to K, and C is also congruent to B, and that means AB inverse belongs to K. Okay, what do we want? We want to show that Ka is the same as Kb. They are equal. And how can we do that? We can show Ka is contained in Kb or Kb is contained in Ka, but we don't have to do it. Let's use the theorem we already proved, which says two cassettes are equal. Ka equals Kc if A and C are congruent. So here we mean we need to show that A and B are congruent. So I should write here in green before we as more explanation. In this part we want to show Ka equals Kb, and this is I can move this somewhere. I can move it somewhere here, for example. Oops, maybe here. Just I need some space. Okay, So let's go back in green here and make it clear what we wanted to show. That is, we want A and B to be congruent modulo K. Okay, and what does that mean? I want AB inverse to belong to K. So this is what I want. If I can prove that, then we are done. Okay, and can we use this to prove that? I should write here, see? Oops, sorry. It is here, no, excuse me. C belongs to KB, that means okay, come on, are you done now? Okay, this belongs, and this C B C inverse belong to K. Okay, how we get this? Or can we rewrite it in some way? I want to see B inverse. So I want A B inverse to belong to K. Can I use what? Okay, how can I get it? I want to play with that. So in here I may write C equals some K1 times A. In here, because C belongs to Ka, and C here, C equals K2 times B. And then what I get? I get K1A equals K2B, right? And then that gives me multiply by B inverse from both sides. Then I get A B inverse. Okay, I have K1 here equals K2. Now multiply by K1 inverse from both sides. Then I get A B inverse equals K1 inverse K2, and that belongs to K, and then we are done. So just playing with it. This is what we want here. So I did not use this literally. I just used the membership. Okay, and then we are done. We assumed that they are not empty, the intersection is not empty, and then we proved they are equal. Okay, so two right cossets, they are either identical or they are disjoint. That means if you take two different right cossets, then they are, you cannot intersect them and then you get something subset. They are essentially share nothing, or they are actually the same coset. Okay. Okay. If K is a subgroup of G, then what happened here? The union of the right coset of K will give us back G. This is what we are saying here. Like, if we have a group J, actually J will be divided into subgroups. If this is K a subgroup, this will be K plus A for some element, say A1, and we keep doing so. This is K plus A2. I'm saying here plus, I'm assuming the right coset is plus. I'm used to write this. Actually, let's write it in general form. Ka1, or I will say Ka. I don't want to say A1 A2 so that you don't think we will have finitely many of them, and Kc, and so on. So G is the union of right cosets of K, and these right cosets are disjoint. Okay. Now part of the theorem says if K is finite, then any two right cosets of K have the same number of elements. That means the function f from K to its one of the cosets is bijection. So bijection from finite to finite means K and any of its right cosets, they have the same number of elements. So let's prove these two parts. So first we want to show that G equals the union of the right cosets. Okay, so let's prove part 1. We know that Ka is always contained in G, right? Because K is a subgroup of G and A is an element, so multiply them, then the multiplication will stay in G. So for any the coset of any element, the right coset of any element is contained in G. Now we want to show that G is contained in the union. So let me write one more step before I move to this. So I will say here the union, because each right coset is contained in G, then their union, where G can be an element, A can be an element of G, is contained in G. Now what's left is to show that G is contained in the union of the right cosets. Okay, so we want to prove this. We work them as sets. So let G belong to the group. Then simply G belongs to its coset, right? Why? Because the identity belongs to the subgroup. So actually E times G belongs to K times G, because the identity is in there. So we chose an arbitrary element of G and we showed it belongs to its coset. So simply G will be contained in the union. I can write it in here now using small g. Okay, because every element is contained in its own coset. So every element of G is contained in a coset. So all elements of G are contained in the union of all cosets. Okay, now what's about the second part, which is important for us? Okay, what's about this second part? F from K to Ka is bijection. This is simple to prove. Let me write that is a bijection. So is it 1-to-1? Now if f of x equals f of y, that means the map takes an element K and multiply it by A. That means f of x is xa and f of y is ya. Now we are in a group, then we can do constellation, and then we get x equals y, and that gives f is injective. Okay, what's about surjective? This is so direct. Like if we choose an element in here, so it has, so let me say if y equals k belongs to A times k, that means y equals k1 times A for some k1 in the subgroup, and that means simply y equals f of k1. Okay, and k1 is in K, so it is surjective. So the map is bijective. Now if K is finite, here, then Ka is finite. And if we have a function which is 1-to-1 and n2 between two finite sets, then these two sets have the same order, have the same number of elements. So in this case, so let me write that here. If K is finite, if the subgroup is finite, then the order of K, and this is important for us, equals the order of the coset, of the right coset. And the right coset can be any right coset made by any element in the group. So if K is finite, then the order of K equals to the order of any of its right cosets. Okay? And now we will go to the definition of index of H, and we have seen that such a thing. The index of H in G, H is a subgroup. Now it applies the rule of K. Is the number of disjoint right cosets. Now this has nothing to do with the order of the coset, the one we just talked about. Now we're talking about something new, and it is denoted this way. So that means the number of the right coset of H in G. Now if I go back to H and let it be which is R0, R1, R2, and R3 inside the group D4. We called it K. We used to call it K. Now, how many right cosets there were for the subgroup? So we have seen that HD. So to find out the right coset of this, we will just take H and multiply it with any other element from outside it. And the elements from outside it here are D, T, V, and H. Okay. So, but we have seen that all of these gives the same right coset. So we have two different right cosets, and actually we will have the index of H in D4 equals 2, because we only have two right cosets. Now, what about the index of when we took the group to be Z and the subgroup was 6Z? How many right cosets we have there? Actually, we have 6 right cosets. Okay, we can define this index and find it to be finite, even if the group we are working in is not finite. Okay. And if you notice that, and we had talked about it when we learned it, that Z itself is divided as a union of the right cosets of 6Z, the ones we have seen already. Z plus 6Z plus 0, 6Z plus 1, 6Z plus 2, all the way till 6Z plus 5. The intersection of any two of this is phi, and their union, all of them, give us back Z. And I would like to demonstrate this again because this is very important. So let me go back to it. So okay, in here we were working with the group G to be the integers, and the H here was 6Z, or we call it sometimes X and sometimes K. Okay, now simply here Z is, you can see it is simply the union of the right cosets that are written this way, where A is an integer that belongs to Z, and simply this came out to be 6Z plus 0, this is first coset, and 6Z plus 1, and all the way till we reach 6Z plus 5, right? Now this can make us see the theorem more easy. So the union of the left cosets give us the group back, okay? And the intersection of any two of them give us phi. They are disjoint. Okay. And okay, sorry again. And here you see the number of the cosets, left cosets, the right cosets, the distinct ones are 6. Is 6 now. Actually, if I go and ask you now what is the index of Z and 5Z, and then you know what these cosets are, and then you will say this is 5, and if you go back to Z and 3Z, and you will say there are 3 cosets here, And what are they? 3z plus 0, 3z plus 1, and 3z plus 2. Okay, and here is 5 0 plus 1, 5 0 plus 2, and all the way till 5 0 plus 4 plus 4, and 5 0 plus 0. So there will be 5 of them there. Okay, now if the group G is finite, then the index is finite for sure, because we will have finitely many right classes in here and there. If G is infinite, then the index might be finite or infinite. Here the group is infinite. Okay, but the index is finite. Okay, now let's see another example where the group is infinite but the index is infinite also. If we see the following example, if we choose the group to be Q and the subgroup of it to be Z, so we know that we're working here under addition. Z is a subgroup of Q. Now if you take the elements between 0 and 1, okay, I assume we are taking two elements, then Z plus A will never equal Z plus B. Why? Because these are two right coset, and we have seen that for two right coset to be the same, we must have that A minus B belongs to K, right? We have seen this. And now our K here is Z, so if they are equal, that means A minus B or B minus A belongs to Z. And this is impossible because each of A and B are between 0 and 1, and their subtraction is less than 1. It's not an integer. So their subtraction will never be there. So for all rational numbers between 0 and 1, every rational number will give you a different coset of Z. So we will have infinitely many Z. So infinitely many right coset of Z. There are infinitely many right cosets of Z inside Q. Okay, that means the index of Q of Z inside Q is infinite. Okay, now we go to Lagrange Theorem. Which is a very important theorem. If K is a subgroup of G and G is finite, then the order of K divides the order of G. Simply, we are saying here K is finite. If K is finite and G is a finite group, sorry, and K is subgroup of G, then what happens? The order of K divides the order of G. Okay, remember that order of K divides the order of G. The order of subgroup divides the order of a group, and more in particular, what's the division? Let me write it here. Dividing the order of K G over the order of K, we'll say it's divided, right? So it equals some integer. That integer is the index of K inside G, the number of left cosets of K inside G. Okay, and to prove this, so let's prove the first part. Now we have seen that G is a union of the right coset of K. Good. Therefore, that means the order of G is the same as the order of this union, right? But we know that each one of these cosets, all of them are disjoint, okay? And we know that once we have two sets A and B, disjoint sets, then the order of their union equals the addition of their orders. Actually, in fact, in general, the order of the union of two sets is the addition of their order minus the order of their intersection. But we are saying it is disjoint. They are disjoint, so this equals 0. So we got that. And now all these cosets are disjoint, so we'll have the order of Ka plus the order we are assuming K is finite, so we can say write it this way, and then the order of G equals the summation of the order of the disjoint cosets. But each one of these cosets, we have just proved that the order of each one of them is the same as the order of K itself, right? And now we assume that Ka1, Ka2, all the way Kan are the only cosets of G. Let me write this here following this line, where Ka1 all the way to Kan are all the disjoint cosets of K in G. That means the number of cosets of A and G, which is the index of K with in G inside G, is this number, because we are assuming there are n of them. Okay, and now going back here, how many terms we have? The same as the number of the left cosets. So we have n times K. And what is this? The group of G. And what is n? So the group of G is n, which is the index, and in here I must have the order, and then we are done. And this is Lagrange theorem. Okay. Lagrange theorem says the order of the subgroup must divide the order of the group. If we assume, for instance, that we have a group of order 12, then the subgroups, any subgroup of it will have order a divisor of n. So it might be 1, which is identity, or 2, the order of the subgroup, or 3, or 4, or 6, or 12. But be careful here. We are not saying that if there is an integer that it divides the order of the group, then there must be a subgroup whose order is that integer. We are not saying that, okay? We are saying if there is a subgroup of G, then the order of the subgroup is a divisor. So if the order of the group, divisor of the order of the group, sorry. So if the order of the group is 12, then as any subgroup of it must have a divisor, one of these numbers, okay? So this is what I'm saying. Lagrange theorem does not say that their G must have a subgroup of order K for every K that divides the order of G. This is what I'm saying. And an example of this is the group of even permutation S4, which is A4. It has order 12, okay? But it does not have a subgroup of order 6. 6 divided 12, but there is no subgroup of A4 that has order 6. And this is in exercise 44. Now the last thing to do here is the following. We will use this if A is an element of G, then the order of A divides the order of G. The order of A must divide the order of G, where A is any element of A. Now, if the order of G is K, then A to power K gives the identity for every element. So A to power the order of the group will always give the identity. Okay? And let's prove this. For part A, we want the order of A to divide the order of G. Let K be the subgroup generated by A. Okay? And it consists of the identity A square, and then all the way till A to some power R. Okay? And actually then that means the order of K is R plus 1 is R, sorry, which is sorry, the order of K is the same as the order of A. And what is the order? Do we need okay, I'm saying here the order, okay, the order of A is R plus 1, right? Because they are all distinct, we are assuming. Distinct elements, and we are saying A to power, assuming the order of A is R plus 1. I did not need to use this R, but the order of the subgroup generated by an element is the same as the order of that element. So the order of the subgroup divides the order of G. Okay, and order of A equals the order of G, so the order of A divides the order of G. Okay, now what's about the second part? A raised to the order of G gives the identity. So this is part 1, this is part 2. Let's say the order of G equals equals n for some n. Okay, then A is a subgroup of G, right? So the order of A will be okay. Okay, no, I just will say that, okay, order of A just simply divides. I want to use, actually I did not use this, I don't want this because it is already in there. I used it above there. By part 1, order of A divides n. So then we use another theorem. Okay, okay, sorry, order of, if G is K in the theorem, so order of A divides K, so order of A equals Q times K. Okay, so order of A Q times, we want to show, okay, order of A equals Q times, okay, we want A to power K equals 0. I must write here K equals, I must write here K equals Q times the power of A, right? Times the order of A. Okay. Then A to power K equals what? Equals A to power order of A all to power Q, but A to power order of A is the identity. Okay, and we're done. The identity, and this equals that. And this is the end of today's lecture.